The topic for today, hopefully we can touch upon a number of topics that I have in mind. Let's get started with the stacks and queues. And then from there, we will go towards recursions. And then we'll get started with complexity analysis. So we'll see how far we can go. So I thought in order to introduce to the stack, why not we just directly start writing a stack implementation that would give you the best way of looking at stacks. So I just opened a new file, and then we'll try to implement a stack. Now, what is a stack? So let's define what is a stack. So stack is also known as last in, first out data structure. But essentially what stack is a crippled list. So why is it a crippled list? Because what we are doing is that we are taking a regular list. As you saw in this course so far, we implemented list using arrays, we implemented lists using linked lists, and we also compared the advantages and disadvantages of the arrays and the linked lists. But it doesn't matter whether you choose the underlying implementation as an array or a linked list. Stack is a crippled list. And it is a crippled list because you're taking away certain functionality from the list. So it's a crippled list because you are taking away certain functionality. So after taking away certain functionalities, what are you left with? You're left with only three main operations. And what are these three main operations? First is push, which essentially means that you can push a new item onto the top of the stack. Second, what you can do is that you can pop. But pop what? Pop the top item of the stack. And the third operation that we can make it happen through the stack is just examine the, let's call it top. So where you can examine the top item. And that's all there is to stack. So if you want to visualize how the stack may look like, so typically it is drawn like this. So you may have some items A, B, and then on that you can issue a pop operation. And what would the pop do? It will just pop the top item of the stack. So if you pop the top item of the stack, what would be left is simply A. And then you can decide to push a new item, let's say C, onto the stack. And then this is going to just push the new item C, and then now C will show up on the top. Now from here, if you ask, what is my top? Then it would return C as an answer. So clearly you can see that you can easily implement the stack as a singly linked list. And all operations you can see are all done in constant time. So all operations done in constant time. So why is this called crippled list? Because pretty much the limitations of the stack reflect um, how the algorithm is going to work. In other words, the beauty of the stack is dependent on the limitation. So limitation becomes the strength of the stack. So the limitation is what? The limitation here is that you are not allowed access to any element except for the top element. You're not allowed to remove any element. You're not allowed to insert any element anywhere. But just with this limitation, you are able to gain a lot of power. So, so what kind of application can gain out of this? So you can think of a simple problem. Let's say, so let's take an example here. Match parenthesis. So matching parenthesis would look like this. You may open parentheses of different variety. You cannot do that. So you can have a series of such kind of parentheses, and you would like to match the parentheses. So what can you do? So you can scan. So scan through the string character by character. And then if you happen to hit a left parenthesis, then so left parenthesis would mean either you have encountered this or encountered this or encountered this, any of these possibilities. Then what do? You push onto a stack. And if you encounter a right parenthesis, which means like you encountered this or this or this, then you simply pop its counterpart. Of the stack. So pop its counterpart means when you are popping, you check, essentially, you check that they match. So you can imagine, so if you have a stack like this, if you're encountering, so first this left parenthesis, then you encounter this, then you encounter this, and then as soon as you encounter the right parenthesis, you want to pop this out, and you're matching that indeed it matching with um, the the corresponding parenthesis, and then you continue. So now after popping up, you will have this and this, and then you again encountered the left parenthesis. So you push it in, and then you encounter another parenthesis, and then you encounter a matching parenthesis, again you pop it out and you match. So this looks fine. You continue. So you have got this, and then you encounter a square bracket, and then followed by another square bracket. As soon as you got the right square bracket, again you pop and you compare. You found a match. You continue. After popping, the status would be this. And then you encounter a right curly brace. And so we are here. So when you encounter a right curly brace, again you compare and they matched. And then you're left with curly brace, square bracket, and again you match another square bracket. So you pop and it matches, and then you have again these two will match. So you'll push and then pop, and then finally the final curly brace will match. So what is the condition that you actually matched? So first of all, the mismatch can happen in two ways. So first is that there is a mismatch. So when you saw right parenthesis and you see parenthesis of different kind, so mismatch on um, pop, and then second possibility is that you try to pop from an empty stack. So that can happen. So you have more right parenthesis than left parenthesis. So you would be just executing popping operation, because as soon as you hit a right parenthesis, you're trying to pop. And the third possibility is that you get to the end of the string and stack is not empty. In other words, you now have more number of left parentheses than the right parentheses. And if none of these have occurred, then the parentheses have matched properly. So these are the conditions when parents not matched. So you can see with the power of stack is coming out here, just with the ability to access the top element, you are able to gain this functionality of matching the parentheses. So now let's just look at the implementation, how it may look like. So one more operation that could be handy is whether the stack is empty. Is the stack empty? Okay, so what is the first thing that we should do here when we are implementing the stack? what's the first thing that you should do? What are we implementing stack with? So we are trying to use the list, right? The first thing is that you want to include your sll.h so that you have the list functionalities available for you. And then you start writing class stack and then put a semicolon right in the very beginning, and then we can start writing public method here. So we basically need 4 operations here. So push. So what are we pushing here? So we are pushing something. So let's say a val, and so what should be the push operation here? What does pushing into the stack literally mean in terms of the list? If you're speaking, you have to unmute your.
Push at the top of the access front.
So in terms of the linked list, right? So we didn't write down what our private member is, right? So that we should do first. So in the private member, what we have is just s linked list, the singly linked list that we had defined, and we can define m linked list. Okay, now you can tell me what are you going to do. So you have got a list and you want to just offer these 4 basic function. So for pushing, what does that in terms of the linked list mean? What do you do when you're pushing in terms of the list?
You insert a node.
Yes. So what do we do? So dot, you do add front, right? Based on what you have done. So you add in the front eval.
Sorry to interrupt, Professor. Just for context, are you trying to demonstrate that how you would fix the problems with the implementation of a stack for this parenthesis problem, or are you trying to show why it wouldn't work?
No, I'm just going to show you how we are going to implement the stack. So I showed you how you're going to use a stack data structure. I gave you an example where by using the stack data structure, you are able to have a parenthesis matching functionality. Now I'm showing you, okay, how are you going to implement the stack? So we just defined the stack that it's a crippled data structure, a crippled list data structure. And therefore we are taking the list and then we are just crippling it. That's what we are doing. And I just wanted to demonstrate that.
Right. But, yeah, yes, but you wouldn't actually want to use a stack for this particular problem, right?
For which particular problem?
The parenthesis problem. Or this is totally separate from that.
No, I just showed you how we could use the stack data structure, right?
Mm-hmm.
When we are matching the parentheses, because for matching the parentheses, all it needed was just pushing and popping and examining, correct?
Right, but it didn't we just show that it's an inefficient, or it actually wouldn't be able to match all of them necessarily if we have the end of the string without matching all of them?
So I was just showing that if you were to implement this functionality, how the functionality would look. Which part seemed inefficient to you?
Just the fact that you can't, as part of the implementation, you can't actually check each item in the existing stack, so you could potentially miss matching some of them if
no, the point is that for parentheses, you actually don't need to examine any other element except for the top element. That's what I was trying to demonstrate. So, because what are you trying to match when you're matching the parentheses? It's
the left to its right counterpart.
Whatever is the latest scoping you're trying to match, right? And then you remove that whole matched parenthesis and you move on to the next match, right? That's what we were achieving by going through this push and pop process. As soon as we hit a left parenthesis, we are pushing. When we are encountering the right parenthesis, we are popping and checking. These are the only operations we are performing. And then I just listed down under what conditions you will declare that I did not match. So the problem is, parenthesis matching problem is, given, like, think of like you are writing a program, right? And you're only interested in knowing whether there is a syntax error with respect to the parenthesis matching. You don't care about any code that you have written. If you're only caring about whether you have properly matched the parentheses or not, because in C++ language, you're using these parentheses, right? So here I'm showing if that's your problem, how would you do that? And I'm just showing that using stack is pretty effective because you only care about pushing, popping, and checking. That's all you care about. You don't need access to anything that is there internal to the storage. Does that make sense?
Yes, thank you.
Okay. So here now, okay, so thank you for asking the question so that if there was anyone else who did not catch the context, hopefully you get it. So now here I'm showing how we're going to implement such a data structure called stack. So essentially, we take a list and we just strip away the functionality, or we just give only the functionality that is fitting within the definition of the stack. And these are the 4 functionalities. So I just wanted to show you how we can achieve it with the linked list that you have implemented. All right, so after push, you can see push is very straightforward. You just add front, right? So add to the front of the linked list, done. What would be the pop operation?
You remove one from NL and LL.
Yeah, you remove the front again, right? You remove from the
Yeah.
front, right? That's what is making it a last in first out data structure. But are you really ready for that? What is it that would go wrong if you just straight away remove something? If I write, let's say, MLL, see, it's already prompting me what to do. You can see that the first, don't practically need to type anything.
It might be empty.
Can you say that again?
It might be empty.
Exactly. So therefore we need to define, wow, it has already prompted, it's almost read my mind that I need to define is empty. So how do we check is empty? See, it already prompted what I'm supposed to write. It's already checking this. And I'm done, right? So here I would just use, right? I would check if it is not empty, right? If MLL, okay, great. Not empty. Then you remove front. So it's done. Actually, it's better to write other way around. It's better to write if is empty, then you may like to report error, you know. So you might want to call out that there is a problem here. The stack is empty. And you may want to close this. And if the stack is fine, then you are removing and you're done. But here it is wrong. Why is it wrong? Because it is called is empty, not empty. Okay, so what else is remaining? Just examining the top. So int top. So what would you return here? Return what? Okay, you don't even have to speak it out. This is prompting. You just grab the, but is it the top? This guy doesn't have a top method. I don't think there's a top method. There is front method, right? And that's your stack functionality. It's as simple as that. Okay. Any question? So if I were to change this to queue, how would it look like? So let's define what is a queue first. So for defining it as a queue, what we would do, I'm just going to copy paste the entire thing and define a new file, call it queue.h. Okay, so first see how much parallel exists between queues and stacks. So queue as opposed to stack are first in, first out data structure. So you saw the stack is called last in, first out because what came last comes out first when you're popping. But in the case of queue, whichever goes first and whichever goes first is the first one to come out. And that is why it is called queue. First come, first serve basis.
And you mean whichever goes in first, right?
Whichever gets in first comes out first. Yes, correct. So this is also a crippled list. So it has very similar situation here. So it's just that instead of calling it push, it will be NQ, where you are NQing a new item to the front of the queue. That makes sense? Actually, not the front. It should be back of the queue. When you're it's pretty much you can visualize a standing in a line, right? So when you're standing in a line, somebody comes after you. That person is not going to join in the front, but that person is going to join after you if you are the last person. So it's the last. And then instead of pop, this is DQ. So you DQ. Now, where are you DQing from? It's going to be DQing from the front or back? Front of the queue. It's just you visualize a line, right? When your turn comes, the turn comes first for the person in the front. So you go to the back, come from the front. And if you have arrived in the queue first, your chance will come first. And here, instead of calling it top, we will call it front. So examine the front item, and the empty remains still the same. So we'll just quickly change. So this is NQ now. This is DQ. And instead of top, this is the front. So what needs to change here? Who can tell me? Which functionality is actually wrong right now?
NQ.
Exactly. So what should we make this? Add back, which we already have. And nothing needs to be changed elsewhere. Everything else just works as it is. I just wanted to call this queue to be consistent with respect to what we are calling. And we are done with the queue functionality. Isn't this straightforward? So what could be an application of a queue? So one application of a queue is pretty much the practical application as we see. Whenever there is a first come, first serve sort of servicing going on, then what you could think of is the queue data structure. And you can actually imagine why this is a crippled list also, because if you're standing in a queue and there are 100 persons in the queue, and suppose you are standing in a queue for getting a water bottle from somewhere, the person who is giving the water bottle doesn't care about all the persons that are there in the queue, right? He only cares about whoever is in the front. And pretty much it mimics that practical aspect of life. And one of the common ways queues are used is when you have many events to be processed. Generally, they're processed in an event queue because the events are generally processed as a first come first serve on a first come first serve basis. And that's the basic idea. And you will see some more application as we go through data structures later in the course, particularly when we study graph traversal. And there are two kinds of graph traversals. One is called depth first search, another is breadth first search. And this knowledge about stack and queue will vividly come back when we are looking into those data structures. Any question?